The next talk is on Protonospheric Energy Sources by Ralph Cicerone.
Today I'd like to focus attention on two sources of energy for the protonospheric plasma, photoelectrons from the ionosphere and ring current protons. Both of these energy sources manifest themselves, at least in one way, through the downward flow of heat along field lines through the plasma from the plasma sphere into the ionosphere. And evidence of that heat has just been discussed, or that heat flow. Ionospheric photoelectrons play a major role in determining the mid-latitude protonospheric and ionospheric thermal structure, and at least in magnetically quiet times. But at higher latitudes and during special events such as SAR arcs, the energy of ring current protons seems to be involved also. Let me now just sketch briefly what is known and unknown about these two energy sources, at least according to my reading. I won't provide any references or give credit to many people's work who I've run across, but they should be obvious. The photoelectrons, which are important to the protonospheric or plasmaspheric energy budget, are obviously those which can escape the ionosphere and reach altitudes above 1,000 kilometers or so. And the ultimate source of the kinetic energy that they bear is the solar extreme ultraviolet that produces them. The photoionization events which are important to the protonosphere, high altitudes, are those which occur above about 200 kilometers. Most of the photoionization takes place below that altitude, but the photoelectrons so produced really don't travel very far. Their progress is severely limited by their interaction with the neutral atmosphere and ionosphere. The ones produced above an altitude of 200 or 250 kilometers, though, can sometimes travel long distances compared to an atmospheric scale height, as I think was originally pointed out by Bill Hansen. That is, before they lose significant fractions of their initial energy. Some of them can even escape the ionosphere altogether and perform interhemispheric acts, giving rise to conjugate phenomena. Well, what are the factors that limit photoelectron transport and escape and control their energy deposition? Obviously, collisions with neutral atmospheric gases, both inelastic collisions in which the electrons lose energy, and elastic collisions in which they may suffer appreciable changes of direction or pitch angle. There are also long-range Coulomb interactions with the ambient plasma, both of the nearly binary nature and of the collective nature. We've just heard that the fast photoelectrons can excite plasma waves, which are then detectable by the backscatter technique. The initial energy spectrum of the fresh photoelectrons then is modified by these loss processes and softened. The end result is that the energy spectrum of the electron flux escaping the ionosphere looks something like this. I just want to make a few general points here. I have an overlay of many results here. These three graphs here, the histogram and the top dotted line, represent three recent independent theoretical calculations of the energy spectrum of the escape flux. They continue out to about 100 eV. The major points here are that the theoretical computations do agree fairly closely. It's not obvious from this slide, but most of the energy borne by the escaping photoelectrons is borne by the high energy part of the spectrum, although the flux is predominantly composed of low energy particles. Also on this graph, I've superimposed some radar measurements of this escaping energy spectrum. These made at Millstone Hill, and this bar graph region, or this shaded region, corresponding to a large number of unpublished Arecibo measurements of the same quantity. It's difficult to compare these flux spectra for different times and latitudes and so forth, but I wanted to show you a general feeling of what it looks like. The main point here, I think, is that the theoretical estimates seem to be below the measured values. On this slide, I show similar flux spectra, energy spectra of the photoelectron escaping the ionosphere. This measured by Knudsen, a satellite at an altitude of about 560 kilometers above Millstone Hill. This measured by Heikkila several years ago. This curve should be scaled up by about a factor of 3. I didn't do it. I should have. And finally, a representative result from millstone radar itself, just to indicate a rough general agreement in the spectrum. There's not much energy resolution to these experimental measurements of the escape flux. Well, once in the protonosphere, these electrons can deposit their energy in the protonospheric plasma, and there are a variety of factors that control how efficient that energy deposition is. Some of the factors include the fact that the magnetic invariance controls the pitch angle of the electron as it leaves the ionosphere and travels into regions of decreasing magnetic field. There are magnetic mirroring effects. There is pitch angle scattering due to interaction of the fast electrons with plasma waves. There's also energy loss due to these Coulomb interactions. And evidently there is also the efficiency of the whole process depends on the field tube content, as John Evans just mentioned, and evidence seems to agree. This opacity, that is the degree of stoppage of the fast electrons as they attempt to travel through the hemispheric field tube, is a highly variable quantity. There have been a couple of experimental estimates of it with varying conditions and several simplified theoretical treatments, and recently a much more general theoretical study by the French group. It is a difficult thing to calculate. At any rate, it appears that there's enough kinetic energy borne by the escaping photoelectrons to support this downward heat flow, at least if we use the experimental determinations of the escape flux as our estimates of how much energy is being borne upward. The current theoretical estimates of the flux, I think, are low. All of us involved feel that we're limited by inaccuracies in the solar EUV spectrum we use to compute the initial electron spectrum. That also is a variable quantity, but there's widespread feeling that current estimates of this spectrum are too weak by a factor of 2 or 3. Let me pass on quickly to ring current protons. In a non-homogeneous dipole magnetic field similar to the Earth's, there's a so-called gradient drift of charged particles. And the drift motion as such is superimposed on the latitudinal bouncing motion of the particles, and it sees the electrons drifting toward the east and the protons toward the west. I just want to point out a few experimental features of what's been seen in the ring current protons. The location of the ring current changes with magnetic activity according to a balance between Lorentz forces on the current carrying particles and the outward gas pressure. This slide due to Frank, showing an early measurement before, during, and after a magnetic storm of the L location of the ring current, or the maximum proton flux, shows the pre-storm ring current maximizing between 5.5 and 6 or 7 L. Then during the main phase, the ring current intensifying, moving down to an L value of 4, and a progression back towards its original position, recovery in post-storm. Another fairly early measurement reported by Pizzella and Frank is shown here, showing the energy spectrum of the ring current protons. At quiet times, the spectrum seems to be like this, that is, peaking broadly around 10 keV, falling off slowly in both directions toward higher and lower energies. In magnetically active times, the ring current not only moves position but hardens. There is the peak in the spectrum might move to 20 or 30 keV. There are many reports in the literature of these measurements. It turns out that the magnetic field change at the center of the Earth due to the ring current is a measure of the total kinetic energy carried by the ring current particles. Depending on whether the ring current is symmetric or asymmetric, the change of the magnetic field at the center of the Earth can be either positive or negative. Now, this ring current particle energy can find its way into thermal energy of the plasma in many ways, and there are obvious difficulties in following this flow of energy experimentally. Much of the theoretical work has been done in connection with SAR arcs, as originally suggested by Cole. Now, I don't know that this picture is settled yet, but a multi-step process seems to be involved. The ring current protons can excite electromagnetic ion cyclotron waves and turbulence, and electron Landau damping of the waves and the turbulence can then lead into heat for the plasma. There's also a more direct heating of the plasma due to not collective Coulomb interactions with the ambient electrons, the ring current protons. The quantitative story, that is, which plasma physics processes are more important and how quickly the energy can be transferred into the plasma and where it's transferred into the plasma, seems to be very difficult. We're going to hear more about that from Fred Rees and Dr. Thorne, I'm sure. And the factors that control this rate of energy deposition and location depend on a host of ambient properties: the ambient plasma parameters themselves, the location of the plasma pause, the configuration of the magnetic field, the details of the velocity distribution of the protons themselves. I think current theories do agree that there's enough energy in the ring current carried by the ring current protons to energize and continue to maintain SAR arcs as they've been observed. I want to raise two questions I've been unable to find settled in my reading. One is any agreement on the source of energy, the ultimate source of energy for the ring current protons. If someone can point this out, I'd be indebted. That is, what is it that accelerates the protons up to kilovolt energies? Also, I find a kind of questionable use of the characteristic times that Spitzer defined in much of the literature. The characteristic times for deflection and energy loss, I think, could be overestimates in many cases. Thank you. How do you turn this off?
What's not running yet? So, do we have any questions on this? Anybody dare start a discussion?
Challenge?
Well, thank you, Ralph. I have a lot of questions, but I don't want to start it.